Okay, so I'm starting over here. We're going to talk about charging a capacitor. So at t equals 0, what is true? So this is when I close the switch. So there is no charge on the capacitor. That means that it means that there's no voltage across the capacitor because VC is Q over C, which means that VR has to be equal to that full potential of the battery. So at that moment, remember this is still t equals 0. At that moment, the current is that maximum value, right? Because, and so we can actually just write Imax, sometimes again it's called I naught, is the EMF of the battery divided by R, right? Because then what happens? Then the charges start building up on the capacitor. So then, right, Q builds up, which makes VC go up. So VR has to go down because they have to add up to the battery's EMF, which of course means that I goes down. And let me just quickly interject. I apologize about all the inadvertent rubbing of the microphone. That has to be really annoying to listen to. I just figured out where the microphone is. So my bad, guys. I will try hard to not do that anymore. Thanks for bearing with me. Okay, so we have this idea that, so at t equals 0, right, when the current is maximum, and that's because the Q on the capacitor is 0, what does the capacitor look like? The capacitor looks like a wire or a short. You can think of it that way. So for that very brief moment, that's all that's happening, right? Once the charge starts to build up, right, then let's keep going, right? Then Q starts to build up, which means that the current's going to go down, right? And hopefully you're understanding the logic behind this. If Q goes up, then VC goes up, which means like that implies that VR goes down. So that implies that. Oh God, that's a lot of arrows. Sorry. I was just trying to show like a logical flow there. My bad. Okay. So this happens until Q reaches some maximum, and that maximum is equal to CV, and the maximum V is the EMF of the battery. Okay? So, what happens after a long time? That's what we're talking about here, is that it reaches that maximum, okay? And so at t goes to infinity, when the Q is the maximum that the capacitor can hold, right? The capacitor is fully charged, okay? What does that now look like? Here's my R, and now it looks like this. There's a break.
Okay. Spider-Man No Way Home.
My son would like me to leave in the random discussion of Spider-Man's new movie, so we will. Here we are. So when the capacitor is fully charged, that capacitor now looks like a break in the circuit, okay? And so again, even though this seems like maybe silly to talk about now with such an easy circuit, these strategies are going to help when you analyze more complicated circuits. So if we were going to draw some graphs for this situation of the charging capacitor, okay? So let's do Q, let's do V across the capacitor, let's do the current, and let's do the voltage across the resistor. So the charge and the voltage across the capacitor start at 0. As the charge builds up, it gets harder and harder to put that onto the capacitor, so it will reach an asymptote, and that maximal, the maximal value, right, that asymptote is going to be CE, okay, where that E is that, you might see it also just like a V max, right, or battery or something, okay. VC is going to have the same shape, and right, that, right, so this was Q max, this is VC max, right, and so that's of course going to be the EMF of the battery, right? Okay, during that time, right, when the capacitor is getting all charged up, it's taking away that voltage from the whole loop. And so the current and the voltage across the resistor are going to be exponentially decaying. Where did they start? They started at Imax and VR max, where Imax is just the EMF divided by R, because at that, when the Q is 0 on the capacitor, it will look like a wire, okay? So it's just that maximal current is like, it's just a resistor right there, that's all. And then VR max is, of course, that as well. Okay, so we have the shapes, but you know what? Let's actually write the equations. So Q of t is going to be that maximal value times 1 minus e to the negative t over RC. Vc of t is that guy, that's your maximum. Okay, and so this is what the equation for exponential growth look like. Growth looks like is the 1 minus e to the negative t over RC. And so the value in front is going to be that maximal value, right? And then I of t is going to be that maximal value e over r, and then that guy. And the voltage across the resistor is going to be that. Okay. In terms of the actual derivation, there's another video where I just sort of give you the derivation. Maybe I'll make another one where I'm actually giving you, where I'm actually showing you the actual calculus. You know, a little review for air resistance type equations. But with the RC circuits, there's so much more to talk about. And so just recognizing that these are the forms, you can reason through almost anything for RC circuits as long as you understand that the forms that these take. Let's talk about RC for a second. So again, RC is the time constant, also called tau. And you might be interested to see that an ohm times a farad is a second. So that's kind of fun. But anyway, the RC tells you how fast it charges or discharges, okay? And like if you look at one of the exponentially decaying ones, if the maximal value, let's say this is a V of R, the maximal value, of course, is what the battery is, and after a time of RC, this is a value of the EMF divided by, little e, Euler's constant. And so that's about 37%. So the thing to remember is that a bigger time constant means that it will charge or discharge slower. Okay, that's probably good for right now. I'll do a different video on discharging.